History remembers these 8 vehicles and components as disasters, headline-grabbing recalls, congressional hearings, lawsuits that reshaped entire industries. But calling them simple mistakes actually misses most of what really happened. In nearly every case we're about to walk through, engineers inside these companies genuinely understood the risk before it ever reached a customer's driveway. And the real story isn't a lack of technical knowledge. It's what happened after that knowledge landed on someone's desk. This isn't a story about incompetence either. Some of the engineering teams behind these vehicles were among the most talented in the industry at the time, working with the tools, testing standards, and budgets available to them decades before the regulatory frameworks we take for granted today ever existed. It's also worth saying up front that hindsight makes every one of these calls look obviously wrong, in a way it genuinely wasn't at the time. Engineers were working with incomplete data, tight deadlines, and cost pressures from executives who often had no engineering background themselves, and untangling exactly where legitimate uncertainty ended and willful negligence began is part of what makes these cases still debated by historians and engineering ethics professors today. We're going through these chronologically, decade by decade, because watching the pattern repeat itself across 60 years of automotive history tells you something the individual stories alone never quite capture. That this isn't really 8 isolated failures. It's one recurring failure wearing 8 different disguises. Let's start in the 1960s with the Chevrolet Corvair, a genuinely innovative car for its time. America's answer to the rear engine layout European manufacturers had been experimenting with for years. The Corvair's air-cooled engine sat behind the rear axle, and General Motors paired it with a swing-axle rear suspension, a design where each rear wheel pivots somewhat independently around a single point. On paper, that layout offered real advantages: simpler construction, a flatter interior floor, genuine packaging benefits that appealed to GM's cost engineers, and the Corvair earned genuine praise from automotive journalists at launch for how differently it drove compared to anything else coming out of Detroit at the time. But in practice, under hard cornering or sudden evasive maneuvers, the outside rear wheel could tuck sharply underneath the car, causing the tire's contact patch to shrink dramatically and sending the vehicle into a sudden, often uncontrollable oversteer that caught even experienced drivers by surprise, particularly because nothing about the car's steering feel or body language gave much warning before the tuck actually happened. Engineers at General Motors and at competing manufacturers were aware that a stabilizer bar or a more sophisticated independent rear suspension would meaningfully reduce this risk. Similar solutions were already appearing on European rear-engine cars built around the same layout, but GM chose not to include one on the earliest Corvairs, largely to keep costs down during a period when the company was fighting hard to keep the car's price competitive with cheaper imports. It took a young lawyer named Ralph Nader and his book Unsafe at Any Speed to force the issue into public view. And the resulting fallout didn't just end the Corvair's reputation, it directly led to the creation of the National Highway Traffic Safety Administration, the federal agency that still oversees vehicle safety standards in America today. Moving into the 1970s, 2 separate General Motors and Ford stories define this decade, and both come down to the same underlying engineering tension: innovation racing ahead of the testing needed to fully validate it. The Chevrolet Vega arrived with a genuinely ambitious all-aluminum 4-cylinder engine block, a real weight-saving innovation for its era, and one that generated real excitement in the automotive press at launch for its lightness and modern design philosophy, even earning Motor Trend's Car of the Year award in its debut season. The problem was the cylinder walls themselves. Engineers used a silicon etching process instead of traditional cast iron cylinder liners to save additional weight and cost. And that etched aluminum surface simply couldn't handle sustained heat and friction the way a properly lined cylinder could. Engines warped, overheated, and wore out at a fraction of the mileage owners expected from a new car, sometimes needing significant work well before 50,000 miles, with oil consumption and head gasket failures becoming so common that some dealerships kept replacement engines on hand almost as a matter of routine. GM's own engineering team reportedly flagged concerns about long-term durability testing being cut short to meet the Vega's aggressive launch timeline, a schedule driven largely by pressure to respond quickly to growing competition from Japanese imports that were eating into GM's small car market share at an alarming pace. Ford's defining disaster of the same decade, the Pinto, centered on fuel tank placement rather than an engine. Ford's engineers positioned the fuel tank behind the rear axle, a common industry layout at the time. But internal crash testing before the car ever launched showed that in rear-end collisions above roughly 20 miles per hour, the tank could be punctured by protruding bolts from the rear differential housing, sitting mere inches away with as little as 5 inches of structural clearance protecting the tank from the rear bumper. Far less crumple zone than the design really needed to absorb a meaningful impact. Documents that surfaced during subsequent litigation revealed Ford had calculated the cost of a fix, reinforcing the tank or repositioning it, against the projected cost of settling lawsuits from fires the flawed design would likely cause, and chose the cheaper path. A piece of internal cost-benefit math that became known publicly as the Pinto Memo, a document that assigned a specific dollar value to a human life as part of that calculation, a detail that shocked the public far more than the engineering failure itself once it became widely known. It's worth noting that historians and engineers have since debated how much of an outlier the Pinto actually was compared to other small cars of its era. Several contemporary vehicles shared broadly similar fuel tank placement, and some later analysis suggested the Pinto's overall fire fatality rate wasn't dramatically higher than comparable cars of the period. But the internal cost-benefit calculation Ford performed, weighing dollars against a known safety risk in black and white, is exactly what turned the Pinto into the textbook case study still taught in engineering ethics courses to this day. A cautionary tale less about the specific engineering flaw and more about what happens when that flaw gets run through a purely financial lens. Quick pause here because we're only 2 decades into this story, and the pattern is already becoming clear. If you're finding this kind of engineering deep dive genuinely interesting, hit subscribe because we've got plenty more of these historical breakdowns coming, and we're not affiliated with any of these manufacturers, past or present. This is purely a look at the documented engineering record. Jumping ahead to the 1990s and early 2000s, the Ford Explorer and Firestone tire crisis introduced a different kind of engineering failure, one where 2 separate companies' decisions compounded each other in ways neither fully anticipated. Ford specified a relatively low tire inflation pressure for the Explorer, 26 psi in many cases, partly to improve ride comfort and partly to compensate for the SUV's higher center of gravity and resulting rollover tendency, since a softer, more compliant tire helped mask some of that top-heavy handling character in everyday driving. Firestone's Wilderness tires, meanwhile, had their own manufacturing quality issues at certain plants, with tread separation problems that grew worse in hot weather and at sustained highway speeds, particularly in tires produced at one specific facility during a period later scrutinized heavily by investigators. Individually, either issue alone might have been manageable. Combined, Underinflated tires prone to tread separation on a vehicle with a genuinely elevated rollover risk. The result was a wave of serious accidents that eventually led to one of the largest tire recalls in American history, and a very public, very bitter split between two companies that had done business together for nearly a century, each one publicly pointing the finger at the other's engineering decisions. Around that same window, General Motors quietly approved a small parts change to the ignition switch used in the Chevrolet Cobalt and several sibling vehicles across Saturn, Pontiac, Buick, and Cadillac. The detent plunge, the small spring-loaded mechanism that holds the key in the on position, was specified with a spring tension that fell below what GM's own engineers had originally called for. A subtle enough deviation that it passed through the approval process without triggering the alarm it should have. In practice, that meant a heavy keychain, or even just a bump from a driver's knee, could jostle the key out of the run position and into accessory mode while the car was moving, cutting power to the engine and, critically, disabling the airbags at exactly the moment they might be needed most. Internal GM documents later revealed engineers were aware of the problem as early as 2001, years before the eventual recall, and internal investigations at the time reportedly closed without a fix because the cost of tooling a new switch was weighed against the number of complaints on file and judged not worth pursuing. The delay in acting on that knowledge became a central part of the resulting congressional investigation and criminal settlement, and the case remains a frequently cited example in engineering ethics coursework of how a seemingly minor tolerance deviation can cascade into a systemic safety failure. Toyota's unintended acceleration crisis, which dominated headlines just a few years later, turned out to be a genuinely more complicated engineering story than the initial panic suggested. Investigators eventually traced the issue to two separate mechanical causes: ill-fitting floor mats that could physically trap the accelerator pedal in a depressed position, and a separate sticky pedal mechanism in certain accelerator assemblies that could stick partway down due to condensation or wear inside the pedal mechanism itself. Extensive independent investigation by NASA engineers, brought in specifically at the government's request to examine whether Toyota's electronic throttle control software itself was to blame, spent nearly a year combing through millions of lines of code and testing the system's electromagnetic interference resistance, and ultimately found no evidence of the kind of electronic malfunction that had fueled so much of the public speculation and media coverage at the time. It remains one of the more interesting cases on this list precisely because the mechanical explanation, while still a genuine engineering failure worth billions in recalls and settlements, was considerably less dramatic than the runaway computer narrative that dominated the news cycle at the time. A reminder that public perception of an engineering failure and the actual root cause don't always line up. The Takata airbag crisis, which unfolded across roughly the same period and continues generating recalls even today, might be the most purely chemical engineering failure on this entire list. Takata's inflators used ammonium nitrate as the explosive propellant that deploys the airbag in a crash. A genuinely effective and inexpensive compound that helped Takata undercut competitors on pricing, but one that's highly sensitive to prolonged exposure to heat and humidity over years of use. And Takata's original formulation omitted a chemical drying agent that could have stabilized it against exactly that kind of environmental degradation. Over time, in vehicles operating in hot, humid climates especially, that propellant could degrade to the point where deployment sent the metal inflator housing itself flying apart, turning what should have been a life-saving safety device into a source of shrapnel inside the cabin. Internal reports later suggested Takata employees had manipulated some early test data to obscure the scope of the problem from customers and regulators, adding a layer of corporate deception on top of the underlying chemistry mistake, reportedly deleting or selectively reporting test results that would have revealed the propellant's instability years earlier than the public recall eventually came. The scale here dwarfs nearly everything else on this list, tens of millions of vehicles across roughly 20 different manufacturers worldwide, making it one of the largest and most complex safety recalls in automotive history, one that ultimately bankrupted the company responsible for it, and one that automotive supply chain experts still study as a case of how a single component supplier's engineering decision can ripple outward to affect nearly the entire global industry at once, regardless of which brand name happens to be on the vehicle's hood. And finally, rounding out our list with something genuinely different from the mechanical and chemical failures we've covered so far, Volkswagen's diesel emissions scandal, commonly known as Dieselgate. This wasn't a component that failed unexpectedly. It was software deliberately engineered to detect when a vehicle was undergoing emissions testing and alter engine performance specifically to pass, then revert to a different, more polluting operating mode during normal driving, allowing the car to hit real-world performance and fuel economy targets that would have been impossible while also meeting emission standards honestly. Volkswagen's engineers built this defeat device intentionally, a genuinely sophisticated piece of software engineering aimed entirely at deception rather than actual emissions reduction, affecting roughly 11 million vehicles worldwide and resulting in tens of billions of dollars in fines, buybacks, and settlements once regulators uncovered what was happening, along with criminal charges against several individual executives and engineers involved in developing and deploying the software. So, what actually connects a 1960s rear suspension, a 1970s fuel tank, and 2010's emission software, written explicitly to cheat a test? In every single case on this list, the underlying engineering knowledge existed inside the company well before the public ever found out. Someone ran the calculation, saw the test data, or wrote the code, and someone else, often several levels up the org chart, decided the cost of fixing it outweighed the cost of shipping it anyway. It's worth noting how that decision-making structure itself is part of the problem. The people running the actual engineering calculations were rarely the same people with the authority to delay a launch or approve an expensive redesign, and that gap between technical knowledge and financial authority shows up again and again across all 8 of these stories, regardless of decade, company, or country of origin. That's really the through line connecting 6 decades of automotive disaster. Not a failure of engineering skill. These were often brilliant, technically accomplished teams working within real constraints of budget and schedule, but a failure of what happened to that knowledge once it reached a decision that weighed dollars against risk. Modern safety regulation, crash testing standards, mandatory recall reporting, whistleblower protections exists largely because of the 8 stories we just walked through, built specifically to close the gap between what engineers knew and what customers were told, one hard-earned lesson at a time, and every single regulation on the books today traces back to a moment almost exactly like the ones we just covered.